Okay. Okay. So today we'll do some randomized greedy algorithms. It's my second time teaching it. For what it's worth. Okay, so off we go. All right. So I think we've seen a problem like this before. Before we did set cover. This problem is maximum coverage. So again, you have sets and points. Okay. But this time I give you a constraint. You can only take 10 sets, and you want to cover as many points as possible. Uh, Taking at most 10 sets. Okay. So, okay. So this is of course a lot like set cover. Set cover, you're trying to minimize the number of sets needed to cover all the points. And in here, you're trying to cover as many points as possible with a limited number of sets. Last time, or when we discussed set cover, I think we went over why it was NP hard from SAT. Um, why is max coverage NP hard? Yeah, how? Sorry? Case one, case two. Well, why is maximum coverage hard? Or how can we show it? Yeah.
You can binary search on a try to find the smallest number of sets which cover all of them.
Yeah, so if for any particular k, you can figure out exactly the maximum amount you want to cover. Then you just want to find the smallest k that covers all of them, right? So you can kind of do a binary search once you solve this. So you don't have to do a full reduction from scratch. You can just go from set cover, assuming set cover is hard. Okay. So for set cover, we did linear programming, randomized rounding. For coverage, the greedy algorithm is what we're going to study first. And then that's going to set the stage for a randomized greedy algorithm. Okay, so the greedy algorithm for coverage will just repeatedly take the set with the most points. Okay, and it was, I want to say slightly it selects the set covering the most new points. It's not selecting a set cover, but anyway. Okay. One thing I want to point is most new points. So once you take one set, you know, the remaining sets kind of change in value because some points already get covered. Okay, so to make sure we're on the same page, let's run the greedy algorithm on this amorphous thing. Okay. So we want to keep figuring out the set that covers the most points. Okay, we'll see how it does. Okay, that one. Yeah, so up to some ambiguity in what are the sets. Okay, so this one,
Yes.
like that. Okay. All right, what set do we take after that? Maybe this one? This one? Okay, yeah, so it is worth pointing out that we cover 4 new points, and that's what we're really keeping track of. All right, how about now? This one? Okay. Like that. All right, now what? This one? Okay, that's another 4 points. What else? Very left. This one, I think. They're all disjoints. It's not super interesting. Now what? Another 4-pointer here. Okay, now I think we knocked out all the 4s. Now what? 3. Okay. But you get the idea, right? We keep reevaluating which set is the most important based on what you've already covered and what remains. Okay. All right, so that's the greedy algorithm. And the basic question we're interested in is how good is the greedy algorithm for this NP hard problem. Okay. And we're gonna actually abstract this. So what we're going to do is we're going to think about maximizing set functions. Now here's some double notation here, but we want to maximize some kind of function f of s. So take as input some thing and output some score. So So for example, for our coverage example, it's a little bit confusing, but okay, we originally have points and sets in the set cover problem. But now I'm going to have some function f that takes as input a collection of sets. Okay, set of sets is a little confusing when I say out loud, and it's going to return the number of points that are covered by the sets you select. Okay, so these 5 sets, what's f of these 5 sets? It's the size of the union. Okay, sets of sets, a little confusing, but okay. And what we're going to do is going to abstract out certain properties of f, and then we're just going to deal with f. But the nice thing about this f, it'll be more clear once we go over these properties, is that I can capture a ton more problems, perhaps of practical interest. Okay, I'll go over those in a moment. But what are maybe some sort of shooting in the dark, but what are some properties of f? Okay, so f takes out as input some set of elements, it outputs a number. What are some nice properties that we see, at least in coverage? Yeah, a union bound. Ah, okay, so it's subadditive. That's a good one. So in the sense that so f of s is in the case of our coverage problem, if I summed over like all of the individual things in the set S, their individual scores, it'll be bounded above. Okay, we'll actually get a stronger property, but this is sometimes called subadditive. Okay, so that's exactly the kind of properties we're looking for. Like very generic. You can imagine lots of other situations where a function is subadditive. All right. Yeah, so that's also sometimes called subadditive. A union B less than equal to f of A. I guess it's a little bit more general. F of B. Yeah. And then that will give you the previous subadditive we got. Good. That's not actually the problem. We're actually going to get even stronger property, but that's exactly the style of properties we're looking for. All right, what about a simple one? What's f of empty set? 0. Okay, so that's like a nice basic one. Now we want to get some multiplicative approximation. If we want to do multiplicative approximations, we probably want f to be, yeah, non-negative. Oh, okay. Well, all right. Uh, okay. Um, what else? Yeah. Ah, it's monotone. You add a set, you cover more points. You don't cover less in any case. Okay. All right. So we just have one left. That's actually the big one. It's stronger than subadditive. It's not, yeah, quite convex. I mean, it's a word you've probably never heard of before. It's not an ultrametric. Uh, what you say? Strong additive? Oh, because it's stronger than subadditive? Okay, that sounds like if I said that joke, I think half the class would walk out. Okay, so it's called sub. Anyone? It's called submodular. Okay, so let me break it down. This one looks a little bit awkward, but for any two sets, f of A plus f of B is at least f of A union B plus f of A and B. Okay, just sort of uh bizarre. Okay, so before you just said these two are bigger than just this, but now we're also adding f of A and B. Each A and B is a subset of n. So A is in the power set of n because it's a subset of the power set is all possible sets of n. That's why the awkward notation. Okay, let me give you a more interpretable equivalent definition of submodularity. I hate it when I do that. Okay, it's same as decreasing marginal values. So let's go through this slowly. Let's say I have two sets, S and T, where S is smaller than T. And I'm thinking about what happens when I add a new element E. So on the left, it's okay. I add e to s, how much did that increase f of s? On the right, I add e to t, how much did I increase f of t? And this is saying that if t is bigger than s, uh, then the marginal interest increase will be less. Yeah. So this is a probably a phrase you've heard before. What subject does this often come up in? Something like economics, right? Economics. How do you pronounce it? I don't know. But like, okay, so here I have the taco curve. So there's some notion of utility, right? Like how happy you are, and then there's like how many tacos you're eating, right? And at first you're like, that's a great taco, right? Because one taco in, second taco is like pretty good. But after three tacos, you're like, I could use something else. And then at some point, you're sick of tacos, and the more tacos, you actually go down. Okay. But you have this kind of concave curve. Now, this picture is a little simplistic because it's just one dimension of tacos. This is some kind of like discrete notion of concavity, right? Because we're working with sets and stuff. Okay, but you're getting decreasing marginal returns. The second thing is not as interesting once you already have the first. Yeah? Okay. All right. So good. So we're going to analyze first. No randomness yet. Just the greedy algorithm. Oh, maybe I should mention that this general model, uh, becomes very popular. Decreasing marginal returns is just so easy to model real life things with. Right, so you open up like any data mining or machine learning conference or something, they're doing like some kind of feature selection problem where each feature, I don't know, adds some information, but there's some redundancy, so you get decreasing marginal returns. They're selecting features. I don't know, you're making a web search engine and you're selecting results, there's some redundancy, right? So everything that kind of is sort of like some abstracted coverage, there's some redundancy and stuff going in, but you're selecting things subject to a constraint. They all follow into this framework. So you end up, this thing becomes very popular. At some level, we're going to understand when greedy is a good idea, at least from an approximation standpoint. From an exact standpoint, there is an answer to this question. It's matroids. From an approximation standpoint, the answer is some modular functions. Okay, so let's analyze the greedy algorithm first. Okay, so uh, all right, so one by one, let me just go through the notation slowly. You start with an empty set. The first iteration, you look for the first, the element that increases your value the most, right? That's just the first element that's the biggest, the best. And then you add it. And then in the next round, you reevaluate the marginal values of all your elements because they might have gone down because you've already taken an element. Then you get the best one, you add it. Best one, add it. Best one, add it. Okay, so just like before, it's just written in some, opaque notation. And after k, you return whatever you have. Okay, so we're going to just break down the lemma and understand the kind of progress we make round by round. So the first lemma, what's this saying? It's saying that the gain in like round 10 will be 1 over k times sort of the gap. So this is how far you are away from the optimum solution. And it's saying that in each step, you're gaining something proportional to how far away you are. Okay, so optimum is the best over all sets of size k. So it has to do is the best here. You're only allowed to take k elements or k sets if it was coverage, and so opt is the best you can do subject to that constraint. Yeah, yeah. Keep you on your toes. Okay. All right. Does the claim make sense? Okay. So we want to show we're gradually catching up to opt. Okay. So we just go slowly. Make sure it's not okay. All right. So well, I can write it out. Okay. So this is what we're starting with. Right here's the left hand side. Well, so it's bigger than something. Okay. So at some level, what do we know about E? How are we going to kind of relate EI and opt and all these things. So once let me put it this way. Let's say that opt is equal to f of t for some optimum solution t. Okay, the size of t is at most k and stuff like this. Okay, so you took some element. Why did you take that element? You had the best marginal value at that point in time, right? Now your goal is eventually to say, I'm as good as t or somehow comparable to t, right? So it might be natural to point out that this element is in particular as good as any element in T. Okay. Because at some level, it's like, well, if you take something from T, you're probably kind of happy. But if you didn't, you're hoping it's justified. Okay. So for any -1, for anyone that's in T, this thing is true. Okay. Which means I can also take the average and sum over all the elements in T. Okay, so something like this. All right, so just a small thing. This is just saying, well, EI is the best, so in particular, it's as good as anyone in T. Okay. Now, and the nice thing is, okay, we didn't quite get to here yet, but at least we have T on the right-hand side. It seems like that's going the right direction. Okay, so the real question is, how do we start kind of combining this? Somehow I want to get from here to here. I have all these individual contributions, and I'm comparing it to kind of opt up above. So yeah, yeah, okay, somewhere we got to use, okay. Maybe I can give the penultimate line. So towards the end, what we're actually going to do is we're going to directly get f of si minus 1 plus t minus f of si minus 1. This is where it'll eventually go. We'll figure out how to get there. And in the last step, because of monotonicity, this is at least f of t minus f of, I lost a 1 over k somewhere, so I'll bring that back. Okay, so this is how it's going to eventually end. Okay, I just wanted to say that so that we can try to maybe go for this. Okay, yeah.
Modularity with your summation over these materials to get S so I minus 1 plus B is at least S I minus 1 plus T.
Yeah, so let's just say there's only two elements to make it simple. So I'll write f of s minus 1 plus d1 minus f of si minus 1 plus f of plus d2 minus f of s of I minus 1. Is that very helpful? How about this? Just trying to think of the most intuitive way. Let me go back to our notation a little bit. Okay. Now, let me write T, let me just enumerate the elements in T. Okay, D1 to DK. Okay. And then I'm going to write this as, DJ, J going from 1 up to K. Okay. Now, suppose I set TJ to be the subset of the first J elements. Okay. Now, Uh, uh, I mean, maybe more properly write it like this. Okay. So this marginal value is decreasing in Si minus 1. So if I take this set and I add any elements, it only goes down, which is good for us. We're going in that direction, right? Does that help as a hint? So what we'll do is we'll write what we're going to do is I'm going to enlarge that base set by including all the preceding elements from T. That makes sense? Okay, so I've taken this and I've added, if this is the 10th element, I added the previous 9. Things only go down. That's where some modularity comes in. Okay, so now what? What is this? So if we expand that out, this will start looking like f of tj union si minus 1 minus f of tj minus 1 union s of I minus 1. Yeah, sorry, it's a little not the greatest handwriting down here, but what does this let us do? Now you can telescope. Yeah, f of 10 elements minus 9 elements, f of 9 elements minus 8 elements, 8 elements minus 7. Yeah, so they'll telescope, and that's how you end up with this down here. Okay. And then you're done. Okay. All right, so that's that proof. That's fine. Now, oh, I guess we had more white space for it. That's okay. Okay. So, good. Okay, so now given that thingamajig, okay. Is there anything written? No. Okay, so now we want to start taking our lemma, which was sort of just a per iteration analysis, turn it into a global analysis and get a reasonable objective. Okay. So, okay, what can we do? We can take this thing and let's see if we can do this correctly. So what I want to do is I want to keep track of opt minus f of si minus 1, right? So this is equal to f of si minus f of si minus 1. And if we rearrange things correctly, I think our lemma is the same as this. Does that look right to you? Sorry? One sec. First of all, this should be like that. That's important. I'm not saying f of si is opt. I'm saying that first, this term expands out into that different. Does that look right? So it looks like what am I doing? I'm adding you add opt to both sides. Something like this, and then you pull this 1 over k opt on the other side, and you pull.
Eventually subtract from both sides.
Yeah, the inequalities started getting flipped. Maybe if I had written it the other way, it would have been easier. Okay, anyway. This is correct, right?
Yeah.
It's awkward because the inequality got flipped and stuff. Okay, but what can we do with this? If we look at the first iteration, right? Op minus fs1, this is at most 1 minus 1 over k uh, opt, and it's really minus f of empty set, but that's 0. Yeah, only adds what? Well, okay, so that's what that's just a matter of the algorithm here. Question is why? I mean, we're just doing an algorithm that only adds one element at a time. Is that how's that equivalent to? Okay, I think this is getting a little bit confused with the coverage. So, the because in coverage you're choosing sets to cover points, right? And now we've modeled it where each of those e's represents a set. So when I'm adding ei, I'm really taking a set. No, because that's a different n. F is an arbitrary set function over n. Script n. Yes, it's a more general proof. Okay, so it's just some function that takes as input sets and outputs things and has decreasing marginal returns. For that, we're going to show that you always get something. But EI represents one of these elements, which for our coverage would have represented a set. A little confusion in names there. Yeah, so we weren't really taking singletons, and at some level we had abstracted out coverage. Okay, but we're almost done with this initial analysis. Okay. Yeah.
Saying what the lemma is saying. So like when we add the types, I guess elements is better than whatever came.
Yeah, I should have used a better, more white space below, but when you add one element, it's better than any element from the optimum solution, right? And then to get a telescoping series, we actually kind of had that base set with sort of the prefix from the optimum solution, and then everything cancels out nicely.
We're just taking the average for.
Yeah, originally we took the average because it's better than any elements, so it's better than the average of the elements. Okay. Okay, but now it's actually all downhill. So if I look at S1, it's going to be at most, 1 minus 1 over k opt, right? And if you look at S2, you're going to get 1 minus 1 over k of this thing, right? And that'll give you 1 minus 1 over k squared opt. Yeah. You keep going all the way down. In general, if it's Si, this will be at most. We kept going. 1 minus 1 over k to the I opt. Or if I made this k, this would be k. Uh, k plus 1. Oh, okay. Yeah. Gotcha. S2. Okay. This will be at most e to the minus 1 opt by our favorite inequality. Okay. And now we're kind of done, right? If I rearrange things, f of sk is at least 1 minus e to the minus 1 opt. Okay. So this is kind of standard analysis of the greedy algorithm for coverage, but also any monotone submodular function. It would be like lecture 1 in approximation algorithms class. Okay, so that's that. Now, okay, now the actual randomness part starts now. Okay, so So that's monotone some modular functions. The standard greedy algorithm works. It's a little bit analytical, but actually, if you look back, it's only like 3 lines. My handwriting, I think, made it look a lot worse than it was. Okay. Once we got that intermediate lemma, which was just some kind of careful, well, it's better than this, and then we invoke submodularity in this clever way. Then the rest, you just unrolled it, so it wasn't so bad. Okay. So today we're going to be interested in this question of what happens when f is not monotone. Okay, but still submodular. So a classic case is edge cuts. Okay. So f will take as input a set of vertices, and you'll output the number of edges that are cut. Okay. So this is still submodular, and you can think of that on like a per edge basis, right? So before you take any vertices and I look at this edge, taking this edge would add 1 to your score, or taking that vertex would add 1 to your score, taking that endpoint would add 1 to your score. But now once you take one of them, now the marginal value of the other endpoint goes down from 1 to 0, but it goes down, so it's still submodular, but it's not monotone. Okay. So for example, if you ran this greedy algorithm on graph cuts, it would just take all the vertices or something, and then suddenly no edges are cut, right? If k was equal to n, which of course is a little bit silly. Okay. So greedy will not necessarily work in such a nice way when the function is not monotone. And our question is basically, how do we address that? So we're looking at non-monotone submodular functions like graph cuts, but then there's myriad applications out there.
Is the goal to disconnect the group?
No, this would be like you want to maximize the number of edges cut while taking 10 vertices. If we were doing the same constraints as before. All right, so okay, so where did we use monotonicity in our proof? It was only that very, very last line, where after we did that very clever telescoping sum, we get something like, well, before it was t, this is s star, but we got t union si minus f of si, and that's at least f of t. Okay, so we only used it barely at the very end. Okay? And sort of take that part for granted. And when f is not monotone, you can't take that last step. Okay, yeah, question.
Somewhat similarity of like implemented monotone.
Yeah, I guess it doesn't. Here would be that counterexample. Graph cuts is submodular, but if you keep adding vertices until you take the whole graph, you're not cutting any edges anymore. So f of everything is back down to 0. Yeah.
So when we choose like 2 races, then we just cut all the edges that connect between these 2 races.
No, so you take some vertices and you only get points for the edges that have exactly one endpoint in your set. So once you take both of these, you get 0 points for that edge because you're not cutting it anymore. Maximum total number of edges cut. So edges inside here, you don't get points for.
Wait, since it's so long, we're gonna just do the cases on like 183 or for each edge.
Yeah, so to prove this is submodular, you can think of this as like a sum of submodular functions, one for every edge, just a 0-1 function for every edge. And a sum of submodular functions is submodular. Okay. All right. Okay, so okay, good. All right. Okay, so we're trying to deal with this non-monotone case. Okay. Where this relatively simple greedy analysis, I feel like I didn't make it look as simple as it should have been, won't work. And it's just this last silly step where we normally say, well, take too many elements, it doesn't hurt you. Okay. So here's going to be our key lemma, and we'll explore its consequences and then we'll go back to proving it. Okay. So what we're going to do is we're going to shift from just evaluating sets to evaluating random sets. Okay. Suppose I have some random set R, then I can ask, what's the expected value of f of r. So r is some random set. It can be this one day, that another day. What's the expected value? Yeah. Oh, not a question. Okay. Um, so this lemma says, okay, suppose you're promised, f is some modular, and suppose you're promised that every element appears in your set was at most probability p, like maybe 1/2. So you just promise that any element only appears in your set was probably at most 1/2. Okay. And then our key lemma says f of r is going to be at least 1 minus p times f of the empty set. Okay, now this might seem unappealing because we're used to that being 0, but give me a moment. So well, if p is 1/2, so if every element appears at most 1/2, you get at least half of the empty set. Okay, that seems like 0, but actually this doesn't really require things to be normalized. So let's look at this. Okay, so in our case, right, we have some set Si, and this is sort of looks like the last line of our proof. And suppose we change our algorithm somehow, and I promise you that every element can appear in Si with probability at most 1/2. Then I'm claiming that the expected value of this union, this thing that we couldn't deal with before without monotonicity, is going to be something useful. Okay, but what? What would go here? And why? You can guess the what, and then we'll figure out the why, but
So average.
well, this is an average.
Weighted average of S.
Okay, 1/2 f of s star, that is the right answer. Why? Okay, don't ask you why. Great. Okay. How can we use this lemma and apply it to get something like this? Now, some things check out, type check, right? Si is our random set, S star isn't. And every element appears with almost 1/2. So we just kind of like dropped Si and we kept the 1/2 there. But obviously you're looking at say, oh, that's empty set and this is f of s star. So how can I make this, how can I obtain this from some kind of f of empty set sort of statement?
Doing on all the elements that are S star.
Do it on all the elements that are not S star. I'm not sure if I know what that means, but I'm thinking of maybe like, instead of trying to apply that lemma directly to this f, can we think of like a surrogate or auxiliary? Yeah. Okay. F of S union S star. That'll still be a submodular function. Okay. So we can apply the lemma to this, and now G of empty set is f of S star. Okay. All right, so this f of empty set is actually more useful than it looks. Okay, good. All right, so now we want to prove this lemma, and then we'll figure out how to maybe incorporate it cleverly into our algorithm, right? Because this will kind of help us. Now you can start imagining how to address the last step of our analysis. Okay, good. So here's a very nice. We're going to do a very nice proof. We're going to introduce a nice idea. Okay, so we're working originally with set functions, discrete functions. Okay, and compared to even like integer programs or something, this one's a little bit more opaque, right? Because it's sort of a black box and assigns values to sets. There's some rules constraining it, but you don't know much about the machinations. And what we want to do is we want to do a continuous extension of this function. So what does that mean? Think of like if there was 3 elements, think of like a hyper, three-dimensional cube, right? The corners represent sets. Maybe this corner represents just the first element. That corner represents just that element. And then, so different corners will represent discrete sets. And everything in between is some fractional thing, 0.5 of this element, 0.2 of that element. Okay? And you can think of the original set function as giving you definitions on all the corners. Okay? A continuous extension is any kind of function that sort of fills in the square and agrees on the corners. Okay? So we're going from f of s to capital F of some vector x. But whenever x is the incidence vector of some set, you know, a corner of that hypercube, it should be equal to the original set value.
Vector.
Incidence. So this means like it'll be a bunch of zeros and ones, but only if it's in the element s. So it's just going to indicate that it's in the set s. Okay. So in other words, we're taking something that's kind of naturally discrete, and we're going to see what we can get from taking a continuous point of view. Does anyone want to? Can anyone think of a way a natural way to maybe define one such thing? Yeah.
You do expect the value when you choose each element to be the set and probably correspond to it.
Okay. So here's a natural definition. So I can take my vector x, which is assigning values between 0 and 1 for every element. And I'll think of those as probabilities, 0.3 of this element, 0.2 of this element. And maybe in the simplest case, I'll say, well, let me get an independent sample. Okay. And where probability that E is in S is equal to X sub E. And I'll evaluate what's the expected value of this set. Okay. So that means when X starts to look like a ones and zeros vector for some elements, there's no randomness left, right? Because this element's always in, that element's never in. And then so you recover exactly your underlying set. Yeah.
Sorry, just to clarify, we're trying to make F continuous.
Yeah, we're trying to extend it continuously to the whole kind of, instead of 0 or 1 to 0 to 1.
That's continuous because the domain is like
This function will actually be continuous in the other sense of the word, but I think they originally just called it continuous because you're defining it over the continuous space. The domain is continuous, not discrete, but this function will also be a continuous map because it's going to smoothly change in XE. Okay, so good. So that's called the multilinear relaxation. That's one that has many applications. That's not the one we're going to use because it's each dimension is linear on its own. But that's not the one we're actually going to focus on today. We're going to look at one that I'm going to first define it abstractly. It's called the convex closure. So we're going to kind of still take the same recipe where I'm going to try to think of some kind of random set where the marginal values are given by the input, okay? So you're taking as input your vector, now I'm calling it P because I'm thinking of it as probabilities, and you get to choose a random set R, okay? And it needs the margins need to agree. Probability of an element being in the set should be equal to PE, okay? But otherwise you want to minimize the expected value of this random set. Okay. Now, just because you're doing this, you'll automatically do get that extension property. It's going to agree on all the corners of the hypercube. So any distribution that, you know, the margins match is going to be okay. But maybe you don't want to do an independent sample. Independent sample is valid, but now you can maybe make things correlated, anti-correlated, whatever you want, and you want to make this as small as possible. Yeah. What is what?
it's a minimum take.
Oh, infimum. It's like min, but fancier. It's just min. It's a compact space, so it's going to attain the. You're minimizing the value. You're choosing R to minimize it. And so F minus, yes. This is like a magical function that says, well, imagine you can just figure out the smallest R. Smallest R does exist because it's a compact space of distributions. R is over a compact space, right?
Well, domain of F is
You gotta specify. It's fine. Never mind.
No. The space from which you're choosing the distribution, the set of all distributions of random sets is compact. Because it's a finite thing.
Oh,
Okay, okay, so my question to you: when f is submodular, how would you choose a random set to minimize this value? What do we know about submodular functions?
aren't we choosing a random set? That doesn't seem very easy.
So this is a definition. So this is some continuous extension called the convex closure. By definition, it tries to choose a random set that minimizes the value. The nice thing about this random set, if you do a random set that matches on the margins, it is always a continuous extension because it agrees on the corners. Because once you get to the corners, it's 1 or 0, and there's no randomness left. So it's a natural way to get a. And I think actually any continuous extension can be interpreted like this. So it's kind of one to one.
The expected value of that.
Well, you get to pick the distribution of sets. So R is referring to a distribution, right? You get to design a randomized set, and the rules are for each element, the odds of it showing up in the element has to match that input coordinate. What? Probability E is in R is equal to P sub E for all E, for all elements E. Yeah, P is a vector. It has a value for every element. It was called X in the previous slide. But now that I'm thinking of its probabilities, I replace it with P. Okay. So it has a 0 fractional value for every element. Okay, so getting back to the question, if you want to minimize a submodular function, right? So you have to kind of choose some kind of random set. Some elements have to appear more than others. How would you want to minimize the value?
The middle.
Yeah, what does in the middle?
We need to achieve it.
It's a you're choosing lots of elements. I don't know what the middle or the mean refers to.
So we follow up on that probability.
The probabilities are given to you. It says, oh, this element has to appear as probability 0.1. That element has to appear as probability 0.3. So one possible choice of R from the previous slide is if you had done an independent sample, right? Every element independently appears as a given probability. The question is, can you do better from the standpoint of minimizing? Okay, so what are some of the defining things of submodular functions, right? So when you look at something like decreasing marginal returns or f of a plus f of b is at least f of a union b, or even just from the perspective of coverage, right? Okay, so let's say you have two sets and you're required for them each to appear with probability 0.5, right? How do you want to make them appear so that the average union is as small as possible?
And then opposite.
Right?
I feel like don't you want to be disjoint mostly?
So okay, so let's say you have two sets that each need to appear with probability 0.5, you're doing coverage. If you made them separate, then they'll never overlap. Half the time you show this set, half the time you show this set, and they'll never overlap, right? So you're kind of maxing out each of them. Okay, we want to do the opposite. We want to minimize the function. So you want to start maybe making the elements overlap and co-occur a lot, right? So decreasing marginal returns is saying something like, look, having them kind of separated always better than kind of aggregating them together, right? So decreasing marginal returns, if you're trying to decrease things, just pile them all together as much as possible, intuitively. That makes sense. So if you have some solution, I have some fractional coverage solution, 0.1 of this set, 0.3 of this set, 0.4 of that set. The worst case is when all the sets are completely correlated, because then they'll overlap each other the most.
So do we just choose a Gaussian distribution?
No, yeah. So what would be a distribution then that maximizes overlap, maximizes correlation while respecting the margins? Yeah.
Same from 0 to 1 of that slide.
Yeah. So this was observed by Lovatz. It's a completely correlated rounding. So what are we going to do? We're going to pick some value t between 0 and 1 uniformly at random. Okay. And then I'll take all the elements PE that are greater than or equal to T. Okay, so that's going to correlate them as much as possible and just stack them on top of each other. Yeah, and the full set of sets you take will kind of form like a chain. Make sense? Okay, so with this, we're going to try to okay, so we want to prove this thing is in fact intuitively based on my examples, it might seem like that's the right solution. How would you do this formally to prove it? Okay. So okay, let me start with some simple observations. This random set ST, so I mean you choose T and out comes some set based on T. It's a chain, right? You have both the sets it can output, its support is a nested chain. And it's not hard to realize that it's the unique chain, kind of chain-like random distribution that respects the marginal. There's no other way to do it. Okay. So now if we can just say, okay, suppose I have some set R that purports to get the infomode. And if I can show that R must be a chain, or rather I can always turn R into a chain, there's only one chain that respects the margins and we're happy. Right? So if I can just show that whatever does work, is a chain, or I can gradually turn it into a chain without increasing the value, then that unique chain kind of Lavat set is the solution or a solution. Yeah, so what I mean is that the sets it outputs, they're like nested.
Like doing this.
A chain of sets, an increasing chain of subsets. Yeah, the support forms a chain. The sets that it can, the literal sets that it can be. Yeah. Okay, why? Or how do we prove this? Okay, suppose. So by when I say R is a chain, I mean the sets it can take on as a chain. So suppose not, right? So that means that maybe you have two sets A and B where they're properly intersecting, right? So A and B is not empty set, and then A is not a subset of B, and B is not a subset of A. Okay, so you have two properly intersecting sets A and B. Okay, and they each have some positive probability. So let's say this has some probability P, and this has some probability Q, and let's say P is less than Q. Okay, now they partly exist to satisfy uh, the margins, right? So I can't just so what I want to do is I want to modify R so that I have kind of less crossing sets, okay? But I don't increase the value. Yeah. Yeah, so probability that R is equal to A is equal to P. Probably that R is equal to B is equal to Q. Okay. All right, so what do we know about submodular functions? We know that f of A plus f of B is greater than or equal to f of A union B plus f of A intersection B, right? So what does that say? Okay, if I take this and I decrease the probability by P, I also decrease the probability of this set by P. Originally the curve was 0.1 and 0.2. I'm going to subtract them down. And I increase this probability by P, and I also increase this probability by P. The margins will still be respected, right? So if I have some element that appears in A and B, it's going to, if I decrease the probability of A being output by P, it'll go down by P. If I decrease the probability of B being output by P, it goes down by P. But then it goes up by P, it goes up by P. So down P, 2P, up 2P. If it's not an intersection, if it's only in one of them, you'll go up here and you'll go down on just one. So you still respect the margins this way. But at some level, you've sort of uncrossed your solution. Your value only went down, it didn't go up, but you've gradually uncrossed your solution. Okay. So in particular, what we can do is we can, if you just want to like make the proof end quickly, maybe you want that, you know, among all possible R's that attain a minimum value, choose R that maximizes the expected cardinality squared. Any convex function will be fine. Yeah. And here, because you get to square a bigger number here, the expected size will actually go up from uncrossing, which will be a contradiction. Okay, so if R is actually truly maximizing the cardinality squared, you shouldn't be able to uncross anything like this. So R must be a chain. Okay, so there's always a chain solution. That means the Lovat's kind of correlated set is an optimum set. Yeah.
Like we meant that like if we decrease A and increase B, then A will be A go up, I think.
Yeah, so R is a distribution, right? So R you can think of as, you know, it's just defined by a bunch of probability. What is the probability that R is equal to A, R is equal to B, and they all have to add up to 1. And so here are two sets that are in the support of R. They occur with some probability P and Q, and let's say P is less than Q. And what I'm going to do is I'm going to modify R. I'm saying, okay, you know, A used to occur with probability P. I'm going to decrease that by P.
So it's not zero.
Then it's now 0. And I'll also decrease B by P. Okay. And on the flip side, I'm going to increase A union, the odds of it being A union B by P, and the odds of it being A and B by P.
Because these are all distinct sets. So
Yeah, they're all distinct. Yeah. And the value doesn't, yeah, that's where they're properly crossing and stuff. Okay. And here, you know, you lose this, some percentage of this, some percentage of this, you get back the same percentage of this and same percentage of this, and your expected value is only going down because of the square equal sign. But meanwhile, you maintain the same margins. The odds of each element occur stays the exact same. If it occurred in A and B, it's going to get both of these. If it's only A or B and not both, you know, it'll go down by P on one of them, it'll go up by P on the other. Okay, so you can always uncross things without increasing the value. We took two crossing sets, we uncrossed them. Okay. All right, so fine. So if you know that, can we now use what we learned, this trick about the convex closure, to finally prove this? So this says now for any random, so the power of this lemma that we need for our proof, to go all the way back to greedy. The power of this lemma is that for any random set, was a promise that any element occurs with some most fixed probability p. This is now just a scalar again. Okay. Then the expected value is at least 1 minus p times f of the empty set. How can I prove that using kind of this Lovat's trick and convex closure stuff?
It's like
Yeah. Okay. So let's say that x is equal to we'll make a vector x, which is the probability that e is occurring. Get the margins right, and then that'll give us our set st. Okay. So we know that the expected value f of r is at least, because the worst possible set was these margins, is this particular set that maximizes all the overlap. Okay. Now we just have one more step. So if we expand out this thing, right? What's it actually doing? You know, it's f of some set, f of some other set, f of some other set. Plus, how often is it at least the empty set? Whenever you choose value t that's greater than p, it's the empty set, right? Plus some 1 minus p f of the empty set. Okay. So all of this is some non-zero stuff that you just ignore and drop. Okay, so you always get at least some fractional value of the empty set. So the Lovat's set is the worst set, and now worst set is empty some amount of time. Yeah, it's very clever. Yeah. Is it better to change the notation? The answer is almost certainly yes. Uh, yeah, yeah. Yes, but why did you ask this lecture and not any previous sentence? Why start now? Yeah, I agree. It's of course crazy. It's, yeah. Okay. All right. Maybe I should. Okay. Before I reveal the actual algorithm, here was our old algorithm, right? Our old algorithm was not randomized because it just deterministically took the best element every time. Okay. Now I want to drop monotonicity. Okay. Uh, and we want to use our lemma. So any fun ideas for how to maybe jigger the algorithm a little bit? I want to kind of limit the probability of any element being added to my set. This is maybe the one fun part of class where you get to design an algorithm. The one fun part. And then back to some bleak analysis, straight into studying for the midterm. And you guys are gonna love me when I'm back from my trip. Okay. Well, we finished coming up with the questions today, so we think it'll be great. Okay. Okay. Any fun ideas for adjusting the algorithm? I kind of want to do something sensibly, somewhat greedy, right? I still somewhat want to take the good elements, but somehow we don't want it to be deterministic anymore. Yeah. Make a probability proportional to cardinality. Well, let's maybe just expand out concretely what you mean. So let's say in the first iteration, you found the element that looks the best. Any other ideas? It's fun to think about before I show the next slide. Okay, so maybe half the time you take the element and half the time you just take something random. Yeah, or maybe even nothing at all or whatever. Yeah, that's reasonable. Now, one thing I want to maybe be a little careful about. One thing I'm worried about. The first element, so you find the best element, right? You either take them, or if you don't, you take something random. Say it's completely useless. You know, I throw a bunch of junk elements that don't do anything. It's the same as taking nothing. Now, the next round, you get the same element because it still looks really good because you added junk last time. That doesn't change anything. The next time you flip another coin, right? So suddenly the odds of this one element not being taken goes down to like 1/2 to the k because you have to get tails every single time. Plus, in that case, you haven't taken any elements, which isn't great either. But so that scheme actually won't necessarily help you bound the amount you take an element. Yeah. Yeah, so maybe we can just adjust it where if you don't take the first element, you just throw it away forever. So maybe you find the best element, it's probably one half you take it, there's probably one half you just chuck it out the window, and you don't even look at it in later iterations. Then you kind of get one half, and yeah, I think if you push that through, you might get like a 1/4 approximation or something. Yeah. Okay, well did you see those lecture notes? Okay, well, that's quite keen. So I do think that the thing where if you do one half take, one half throw away, will get you a 1/4 maybe 1/4e or something. I mean 1/4 of what we got before, so maybe 1 minus 1/e divided by 4. I'm only guessing because one you throw away half the value each time you chuck it out the window, and then you're going to lose another factor of 2 from our lemma. Okay, so I'm guessing you might lose a factor of 4. We're going to try to do something a little bit better. So what we're going to do in each iteration is we're going to gather up the best k elements with respect to their marginal value. Okay, and then we'll choose one of them uniformly at random. And this time I got the subscript correct. We'll add it to our set. What's the intuition? Why k? Or maybe advancing here. What should I do for the first line? Or actually no. Okay, let's just start the analysis in the interest of time. Okay, so I want this is the expected gain, right? Maybe conditional SI minus one. Imagine SI minus one is fixed at the moment. And you add some random element. So let's just first break down how should I expand out sort of that expectation. Yeah, so you're choosing one of these guys from Ri, right? So here we just have summing over 1 over k, the sum of ei. Okay, so this is just choosing one at random. So I think maybe this next part is where my question, oh man. Okay. I hope you didn't look too closely. All right, so now coming from here, how do I at some level relate to T or S star? I think the analysis is going to use S star, but. So I know the first one is at least as good as any one in opt. That was our logic from before. The problem is that now I've taken a top k. How can I relate the top k to elements from opt? So before it was easy to say the best element was as good as anyone in opt. Yeah. It's better than the top k in opt. And in particular, how many are in opt? Okay. Okay. So choosing the best k elements out there is actually better than all of the elements in opt. Because opt represents k elements out there, and you chose the best k. Yeah. Okay, so you get this, and then what? Well, this looks familiar, right? This exact term came up before. It's just that we didn't have to go through this, right? So from here, we can do that same telescoping trick. Okay, so I'll skip some of those calculations, go straight to the point. So we get something like this, right? This is the exact same analysis. It's just we had this one intermediate step going through Ri. Okay, so we still get to the same place as before. We haven't lost anything, even though we're not at all taking the best element. Now, okay, and then this is the troublesome term, right? And when it was monotone, we're almost done. This is just bigger than, we just dropped the SI minus. Okay, so now what? Okay, so again, now the question is, can we bound the probability that E is in particular, any particular element E is in our set SI? Like I is 10. How do I bound the probability that the element appears in any particular element appears in S10? What's the worst case? Sorry? 10 over K? Yeah, 1 over K, 1 over K, 1 over, yeah, 10 over K. If we want to be even more precise, yeah, okay. So the probability that E is not in SI, oh, did I do this correctly? Well, let's just go through it slowly. It's not supposed to be hard. Okay, so the odds of it getting chosen in the first one is at most 1 over K, and not getting chosen is 1 minus 1 over K. Not getting chosen in the second one is 1 minus 1 over K squared, third, fourth. Okay, good. So this is correct, right? Yeah.
Is this for any arbitrary elements?
Yeah, any arbitrary element, the worst case, right? It's in the buffer every time, but then it's not chosen was probably 1 minus 1 over K to the I. Okay. And it could be better if it's not even in the buffer. Okay, good. So I'm going to use P there. Good. Okay, so now when I go back to where we left off, okay, that means the probability ENS is at most 1 minus P to the I. Okay. All right, so now what? Is there something written here? Okay, well there it is. Okay, so maybe we could go a little bit more slowly here. This is f of S star union f of si minus 1 minus f of si minus 1, right? Also, there should have been an expected value around here. Okay, and it's to this lemma that we can apply our thingy. Okay, it's at most 1 minus pri, so you get at least p to the I. It's actually si minus 1, so that's why it's p to the I minus 1. Okay, good. Okay, oh geez. Okay, so if I rearrange things, then you're going to get the expected value of f of si minus 1 is going to be, this is a little bit different of a dynamic than last time. P to the I minus 1 over k times opt plus p of e f of si minus 1. Does that match up? Oh, because p is 1 minus 1 over k. Okay, so does this work out? Okay, almost done. We only have a minute. Okay, so let's look at, let's just start unrolling. Okay, so if I plug this in for the first one, I is equal to 1, then what do you get? 1 over k times opt. Okay, we go to the second round, and I guess I already plugged it in. And what do you get? Don't think too hard. Okay. Okay. Now, third one. I guess I'm just plugging in. What do you get? 3p squared over k opt. Okay, we'll keep going. That's the ith one. Survey says I p to the I minus 1 k opt. Okay, keep going. So you get k p to the k minus 1 over k. So the k's will cancel out, of course. And I'll expand out the p, 1 minus 1 over k to the k minus 1 opt. You'll get 1 over e opt. Okay. All right. Okay, so at the end of the day, what did we show? We showed a 1 over e approximation. Okay. For general non-negative submodular functions. Okay, you guys are lucky I prepare ahead of time. Okay. That's right. Okay. Now you can fraud my signature. Well, you can tinker with it and see if you can do better. I think within this framework I have, and k is the best I could do, but I think you can just like set it as a variable and find out for yourself. You can do slightly better than 1 over e. So it's a huge pain, but it's sort of an open question. Trying to get 1 over e plus 0.0000. But there's like proof of concepts is not the best possible algorithm if I'm not mistaken. Okay, but yeah. Okay, so that's it. That's randomized greedy algorithms. The real focus was on submodularity and this correlation and kind of minimize certain random sets that minimize the value. And yeah, good luck on the midterm.